Welcome to today's video. Today we're going to address the mysterious stress-energy density, stress-energy tensor that was postulated to exist in postulate 2 of general relativity. Now remember, postulate 2 didn't tell us what this stress-energy tensor has to be, but postulate 3, Einstein equations, does tell us in a way how to build the stress-energy density of anything from first principles. Now, let's get a little bit of a look into it, revisiting a little bit the notions that we introduced in special relativity when we talked about Hamilton's principle, now in the context of general relativity. An important distinction between different objects that are commonly referred to in field theory, it's fundamental here for us. Now remember that an action can be written as the integral over some time parameter of a Lagrangian. We can go one step beyond and say, well, but I can maybe think of what is the Lagrangian density so that the action is given after I integrate over the whole of space-time. Over the whole of space-time. So, you see the difference between the Lagrangian and the Lagrangian density. These two things are equal, and you can tell, given a set of coordinates, that you can get the Lagrangian by integrating over space. So if you have a set of coordinates dx, dy, dz, dt, then you know that you would get the Lagrangian doing the three first integrals between, like, with respect to dx, dy, dz, right? You get the Lagrangian integrating over the spatial volume. All right. There's another object that we can define that is the Lagrangian weight, and you can tell that the Lagrangian density is going to be the Lagrangian weight multiplied by the minus determinant of the metric. The reason we do that is because under changes of, imagine a change of coordinates. For example, the change of coordinates, we already saw that this element of volume would transform with the Jacobian determinant, as you remember from calculus, and as we also saw in our calculations in this course. And the determinant of the metric, if you remember from the last exercise we solved in differential geometry, transforms with the square of the determinant of the change of basis matrix, the square of the Jacobian. But the transformation is precisely the inverse to this one, so they cancel each other. In the end, you have a square root that cancels the square that we had when the determinant transforms to a different basis. And the Jacobian determinant here and the inverse Jacobian determinant here, they cancel each other, and this whole thing is invariant on the changes of coordinates. That's the reason why it's very convenient. And why so? Because it's very convenient for first principles to write the Lagrangian responding to fundamental principles of physics when you factor out kind of the determinant of the metric outside in the element of volume. This is all a matter of, in a way, ultimately, it's a matter of convenience and convention. And I really hope that you don't get much confused with it. You can just think about it at this level as, yeah, we can write the Lagrangian, or we can think of a Lagrangian density, which is what you get when you integrate over, you get the action when you integrate over the whole of space-time. And that makes sense when you're talking about something covariant. It makes sense to write it like this, as in not distinguishing a particular parameter. And then there's a way to write it so that this element of volume, now I write the invariant element of volume, something that doesn't change and the changes of basis. Now we can ask the following question, which is the question that Hilbert solved. In fact, I would recommend you read a little bit more on that historically, because there's a little bit of controversy between who was the first person who developed general relativity. Hilbert simultaneously was developing a formalism that actually yielded Einstein equations as well. I recommend you read about it. It's a very interesting chapter of the history of physics, and a topic to discuss more about and to read more about. The postulates of general relativity tell me that there has to be a stress-energy density, but I don't know it, and I don't know in principle how to build it. Even though I do have the ingredients in the postulate, but in mine I don't know. What I know how to build is Lagrangians, and in particular Lagrangian weights and Lagrangian densities. So if I know the Lagrangian densities or the Lagrangians for matter fields, what is the action that will yield Einstein's equations? You can ask that. And then you would say, okay, that action is going to have to be, when I have an action that is going to give the equations of motion for relativity for both matter and space-time, I'm going to say that this thing is going to be some, let me just write d for x, right? So this thing is going to be some Lagrangian density, I'm going to write like that, Lagrangian density for gravity plus some Lagrangian density for matter. So this is a reasonable assumption. I can have gravity without matter, and I can have matter without gravity, so it makes sense that the action is going to look like something like that, right? Okay, So then you can wonder, okay, what is the form of this Lagrangian density for gravity so that I recover Einstein equations? All right, let's see it. This is the action. So this action that I wrote here tells me that let me write with the letter M. Let's do it here too. For matter, let's just write the letter M, just to reduce the cumbersomeness of the notation. So what I did here is I wrote some Lagrangian from gravity and then added the Lagrangian weight. For convenience, I put the minus determinant of the metric outside, so I'm talking about Lagrangian weights. So this thing would be the Lagrangian weight associated with gravity. This is the Ricci scalar, this is Newton's gravitational constant, and this is the Lagrangian weight from matter that you know from your first principles for matter. You may say, okay, is that really true? We can use Hamilton's principle from this action and then find out what are the Euler-Lagrange equations associated with this action, and we do it like this. That is Hamilton's principle. Now, of course, that implies that when I vary the action, the variation with respect to all the possible things that can vary is going to have to be zero. In particular, imagine that I want the equations of motion only for gravity. I mean, I could get all of them from Hamilton's principle, of course, for matter and for gravity, but let's focus on the ones for gravity. Now, I'm going to consider the dynamical variables that can change, the metric, and I'm going to demand that the variations of the action with respect to the metric are zero. So I do this, like this. So the variation of the action with respect to variations of the metric, in this case the inverse metric is what I picked, is given by that, right? That's trivially applying variations. Now you may ask, why do you take the inverse metric and not the metric? Which is funny that you ask, because probably if I had taken the metric with the indices down, you would not be asking that, because humans were like that. It would be, okay, variation with respect to the metric. It's the same, it's equivalent to take variation with respect to the inverse metric or the metric in the following sense. So starting from the fact that the metric and the inverse metric, when you multiply them like this, when you contract like that, that gives you the identity. I take variations on both sides. Variation of the identity gives me zero. Then I have this variation here, apply Leibniz rule. Then put on the left-hand side the variation of the metric tensor, and on the right-hand side the variation of the inverse one. Then multiply by g sigma mu from the left. That would cancel this one, give me an identity that I use to change the name of the labels. And there you go. You get that the variations of the metric tensor, the variation of the inverse metric tensor are related like that, which means that something will be stationary with respect to variations of the metric if and only if it's also stationary with respect to variations with the inverse metric tensor. So we are free to choose whichever we think is more convenient. And in this case, it's more convenient to choose the metric tensor with indices up, the inverse metric tensor. And that is because, remember, the Ricci scalar here, it's the Ricci scalar, you get the Ricci tensor, and then you multiply this thing by AB, and that gives you the Ricci scalar, right? So they're going to be explicitly appearing GAB much easier than having to substitute the expressions and get G's with indices down. So it's just very convenient to write it like this, all right? After that clarification, we continue and we expand this as follows, like that. All that I did here is apply Leibniz rule here and divide by the minus determinant of G wherever necessary to be able to factor it out and put it there with the element of volume to make the invariant element of volume. Now, in order for this to be zero, for any variation, this is true for any variation of the metric, same Hamilton's principle derivation of Euler-Lagrange equations, we need that the whole thing here would be equal to zero. And notice that I'm going to write this condition that the whole parenthesis here, the whole square bracket here will be equal to zero. I'm going to write it in two terms. I'm going to have a left-hand side term. That is, I'm going to split it into one term, that is the gravity term, that comes from the gravity, the Lagrangian density of gravity, and the one that came from the Lagrangian density of matter. So because the sum of two things is equal to zero, I'm going to put gravity on the left-hand side and matter on the right-hand side. And that yields me this, like that. So all that I did is equate the square bracket to zero, but put on the right-hand side things related to matter, put on the left-hand side things exclusively related to gravity. So this is kind of cool because that resembles Einstein's equations a lot, right? You have matter on the right-hand side, you have something gravity on the left-hand side. We can keep computing, and we can compute using the following identities. These identities, the variation of the Ricci scalar with respect to the inverse metric is the Ricci tensor, and the variation of the determinant, square root of the minus determinant of the metric with respect to the metric divided by the square root of minus determinant of the metric is minus 1/2 the metric. These two identities are good practice exercises for you. I'm not gonna do them. This one I asked in an assignment the first time that I taught general relativity. They're good practice and I recommend you do it. This one, what you have to do is compute the variations of the Riemann tensor first. From there, compute the variations of the Ricci tensor and then the Ricci scalar. And also realize that the difference between two coefficients of the connection is actually a tensor, as I mentioned in the differential geometry part. That's the trick to doing that. To doing this, there's something called Jacobi identity for matrices, how to differentiate a matrix that is very helpful. I'll write it here as a hint. This is called Jacobi identity or Jacobi's formula, and it tells you how to differentiate the determinant of a matrix as a function of the trace of the adjoint of the matrix and the derivative of the matrix. This is very helpful, and in fact, you use this identity. When I gave you this as an assignment, you and me in previous generations, I first asked to prove that, and then to prove this. Use this to prove that. It's not long, but it's good practice. So I recommend you do this identity. These are the two identities that you need in order to evaluate this. And when you use these identities to evaluate this, you get the following Euler-Lagrange equations. This. So, all right, let's recap what we've done so far. We started from this action. Then we demanded Hamilton's principle, stationarity of the action and the variations of the dynamical variables. In this case, the ones that I'm interested in is the variations of the metric. If I do that, I obtain these equations. Then I use these identities that I told you to check. And with those identities, I got this expression. And this expression, the left-hand side, happens to be the left-hand side of Einstein equations. You may be wondering, well, but you wrote Einstein equations with a lambda g mu nu here, right? Yeah, it's true. The action that I wrote assumes a zero cosmological constant. Exercise for you. Check that if I were to add a minus 2 lambda in here, I would get exactly the same result, but with this term here as well. All right? So let's go back to what it was. We found this, and we know that if this is the left-hand side of Einstein equations, then the right-hand side, postulate 3, has to be 8 pi g, the stress energy density. So look at that. The stress energy density as a function, this is the Lagrangian density. Remember, the Lagrangian weight multiplied by the square root of the minus determinant is precisely the Lagrangian density. The Lagrangian density for matter, that's the thing that you got from first principles, from knowing if it's the electromagnetic field, it would be the electromagnetic Lagrangian. If it were a scalar field, a scalar Lagrangian. We will do it with a free particle in the next step, but this would be the Lagrangian density of the matter fields. Then the stress energy density would be equal to minus 2 divided by the square root of the minus determinant of the metric variation of the Lagrangian density of matter with respect to the inverse metric. And this is the stress energy density. This is, in general, from first principles. The first principles builds you a Lagrangian density, and from first principles we recover this expression for the stress energy density. This is the famous Hilbert-Einstein action, or Einstein-Hilbert action, depending who you ask. And this is this was actually developed in parallel by Hilbert while Einstein was developing relativity. Again, I recommend that you check the abundant literature on the controversy about who started general relativity. Was it Hilbert? Was it Einstein? But this is a completely analogous formulation. Postulating this action would be, if you want, an alternative formulation of postulate 3. Postulating the equations, postulating the action, same thing. The nice thing about doing it from the action is that I can add the matter fields to the action and then get the stress energy density from the matter fields, from the first principles coming from the matter fields, from the Lagrangian density of the matter fields. All right, so hopefully we have understood with this where the stress energy density comes from. We know it exists because we assume, there's an assumption here that the action for the whole gravity plus matter systems is something, the sum of two. The action, it can be written in terms of an integral of a sum of two Lagrangians, one for gravity and one for matter, which makes sense. We have matter on top of gravity, right? And then, assuming there's one for matter, then we find that this thing you knew is the tensor that has to be on the right-hand side of Einstein equations. Now, of course, we also know that this is divergenceless, as the postulate 3 told me. How do I know that this is divergenceless? So this thing, it's equal to 0. How do I know that? Well, because it's exactly equal proportional to the Einstein tensor. And because the Einstein tensor is divergenceless, then I know that this thing is divergenceless, as the postulate says. All right, wonderful. So now that we have understood how to build from first principles this stress energy density, or at least we got an idea about it, let's interpret it. What is the information? What is this thing? What are these locally conserved quantities that are stored into this tensor? Let's try to understand it. Now, the fact that it's called stress energy may probably give you an idea, but for that we need to understand a little bit better. So what we're going to do now is we're going to derive from this expression the stress energy density for a free particle in special relativity, even in a flat spacetime, to get intuition about what this is. And after that, we're going to talk about the stress energy density of a perfect fluid. All right, let's apply what we learned to compute the stress energy density of a free particle, and that will give us intuition that we will use to understand better what the stress energy density is capturing. All right, so I recover, here I wrote the action here, the action for a free particle. Remember that the action for a free particle that we used in special relativity to give the proper equations of motion. This is also the action of a free particle that we got in general relativity, only I didn't add the constants that were kind of irrelevant for obtaining the equation, right? I want the constants here because I want full dimensional results for now, so I recover the constants. Now, I can write the line element parameterized in terms of whatever parameter I want. For example, I can pick tau, being the proper time of the particle, and this is the action. Now, of course, we know that if this is the normal before velocity, so this is minus c squared, so that overall gives me a c that comes here, so then c squared, and it would be just this. But I want to keep the explicit dependence on the metric because I need to take variations with respect to the metric to compute the stress energy density. All right. Now, the problem that I have is that from here, it's very easy to extract the Lagrangian, but I don't want the Lagrangian, I want the Lagrangian density. And remember, the Lagrangian density is something that when you integrate over the whole of space-time gives you the action. Okay, I can artificially add the integral with respect to the whole of space-time, over the whole of space-time, and I do it like this. I just put it in, and if I were to just put it in and write just this, right, you would be like, but hold on, no, you had that, and now you're summing this to the whole of space-time, you're over-summing. No, you just want the one particle trajectory, not the whole of space-time. Sure, I add that, but I also add these deltas. These deltas kill the integral when they're outside of the domain where this has to yield something. So this is literally the same as that. I added an integral over the whole of spacetime, and then I fixed the integral of the whole of spacetime to be only non-zero on top of the trajectory of the particle. For the t, in this, I took a coordinate system to write the volume element here. For the t equals to t of tau, and for the x equal to x of tau, which is on top of the trajectory of the particle. Now notice that the minus mc I put here because I want the convenience of being able to single this out as the Lagrangian density for the free particle. So now calculating the stress energy density is easy because we know that this is going to be T mu nu on Tx, right? It's a tensor field on the coordinates Tx. Remember, this is the Lagrangian density evaluated on the coordinates Tx, that once I integrate it with respect to T and with respect to X, I get the action, okay? So the stress energy density, the stress energy tensor, it's equal to, then it's going to be, okay, 1 over the root of the minus determinant of G. And why don't I write the 2? Because the 2 is going to cancel with the 1 over 2 that you get out of taking the variation of the Lagrangian density with respect to the metric tensor, because inside the square root. So you do get the derivative of a square root factor in there. So that cancels the 2. Also, this cancels this to the minus, one of the minuses cancels that minus. So what you get here is the integral with respect to tau. I'm going to leave some space here because I'm going to write something, and I have a fraction here, and the fraction would have an m and a c from here, x dot mu x dot nu, all right, and then the square root of minus g mu nu x dot nu x dot nu. All right, and of course I have the delta t minus t tau, delta 3 x minus x tau. All right, so that is the stress energy tensor that we get from the Lagrangian density. Now we can start simplifying a lot. Let's assume that we are in flat spacetime. If we are in flat spacetime, g mu nu would be nothing but eta mu nu. And that means that the determinant of g would be x of minus determinant of g would be exactly the minus determinant of nu of eta, sorry, and that is 1, because the determinant of eta is minus 1. All right, if we do that, then this thing disappears. Also, this is the norm of the forward velocity of the particle. The norm of the forward velocity of the particle, this thing is minus c squared, right? Minus with minus plus, this is the square root of c squared. That cancels the c on top, so we get. Now finally, to do the final integral with respect to tau, the easiest way to do it is to reparameterize the integral. Let me find a new time parameter. Keep in mind that this is integrating with respect to the proper time, which is the parameter I chose for writing the action, but I could have written the action in terms as an integral with respect to another parameter. So I can pick a parameter t prime, so that we have that t of tau equals t prime. So I define my t prime like that. And of course, d tau, I can always substitute by having a dt prime here, and I'm going to have d tau dt prime. All right? So if I do this reparameterization, the integral becomes like this, and now I can use the delta function. To do the integral very easily with respect to t prime. That basically fixes t prime to be equals to t. So we get the following. And that's the expression of the stress energy density of a free particle as a function of some coordinate frame, tx, function of space-time. So you can tell that the stress energy tensor is something that only exists on the particle. And then you can tell how it is a density in a way. When you integrate over space, it will give you quantities that are only on the particle. All right, wonderful. Now, let's look at the different components of the stress energy tensor to try to understand what it is. The 0, component. The 0, component has this form. Just substitute it in the expression, the 0, the mu equals 0, nu equals 0. Now, in the rest frame of the particle, this is complicated in an arbitrary frame, but let's consider it in the rest frame of the particle. In the rest frame of the particle, we know that, d tau dt, well, t is tau. If we actually compute it in the rest frame of the particle, t is equal to tau. So d tau dt is indeed equal to 1. And what is dx0 d tau? Well, this is c multiplying the t d tau. And of course, this thing is also 1 because t and tau are equal. T is equal to tau. So this factor is c. So what we get is the following. We get 1 mass c squared. Oh, look at that. In the rest frame of the particle, T00 is the energy of the particle. Well, not quite. It's the energy density of the particle, because is the energy of the particle evaluated along the trajectory of the particle. Indeed, the total energy in that frame of the particle is equal to the integral over space of the stress energy tensor. Now you understand why I keep calling the stress energy density all the time. Integral over the whole of space of mc squared delta 3 of x minus x over the trajectory. Let me abbreviate it as x of t, all right? Now, if you have that, the mc squared comes out, then you have the integral over space of the delta, which is 1, is the area under the delta, which is 1, so it's mc squared. So you can tell that the T00 component is an energy density, right? The T00 component gives you the energy density. It coincides in the rest frame of the particle, is the rest energy of the particle, all right? All right, nice, that's for the 0, component. Let's analyze other components. All right, let's see what the 0j component gives us. I wrote here the matrix structure of the tensor. So we have the T00, which is the energy density, as we saw. And now we're going to look at what's the first row and first column gives you. I mean, the tensor is symmetric, so they will give you the same information. All right, so let's see, we have this. So that's actually pretty easy because we get d tau dt, and this x0 is ct, so we get c dt d tau, dx j d tau. Nice, this cancels this. So what we get here, and of course the delta. I'm going to write the delta 3 on the trajectory, right? I'm not going to write the argument to make it shorter. And I can also play a little bit. Let me just write it here. So that's going to be mc. I'm going to have the delta. Let me just write the delta here. And this thing is going to be dxj d tau. Oh, I can write in terms of the coordinate t as well, derivative with respect to t. dxj dt, but of course I have to pay the price of having dt d tau here. All right. But then this thing I recognize, this is the trivelocity component j, as seen from the frame Tx, the velocity of the particle. And this thing is the instantaneous gamma factor. This is, remember from the videos in special relativity, this is the gamma factor. So what we get in the end is that what I have here is the delta 3 with the arguments C m gamma Vj. And if you again remember the videos from special relativity, this is the jth component of the tri-momentum of the particle. So all that I have here is Cpj, the tri-momentum, and then the delta 3 on the trajectory of the particle. So this is giving me a density of linear momentum with the C to make it units of energy, because we want, or energy density, because we want the whole stress energy tensor to have units of energy density. The delta has units of 1 over volume, and this has units of linear momentum multiplied by C, so energy. Okay? In fact, it's very easy to prove that T0 mu is nothing but C P mu, where P mu is the form momentum, and of course the delta on the trajectory. So here you get the linear momentum densities with the C that make them the same dimension as the rest of the entries of the stress energy density. Wonderful. What about the Tij components? The spatial part contains flows of linear momentum going through some surface. So for example, Tij would be the flow of the momentum component I on the surface perpendicular to the j direction. So this we're going to see a little bit better with fluids. Now, we have seen the stress energy tensor for free particles. Hopefully it was clarifying as to the meaning and how we got it. Let's now see what happens with fluids. Now that we've seen the stress energy density from first principles, from a Lagrangian density in the case of a free particle, let's move to the stress energy tensor for a perfect fluid. Now, there are different ways to obtain it. Ideally, you would have seen a course in fluid dynamics, and from there it's actually pretty easy, because from the continuity equations and from the formulation of an action for fluids, which is not too difficult, it's easy to get it with the same techniques that we've learned. However, I'm not going to assume that anybody here knows fluid mechanics, because, yeah, I mean, come on. Also, I'm not going to derive it in full detail from fluid mechanics assumptions, because I would have to introduce fluid mechanics, and this course has to be finite. Instead, what we're going to do is we're going to use what we've learned about the stress energy density and be clever to determine the stress energy density of a perfect fluid in a particular frame, and from that covariantize it to the stress energy density of a fluid in special relativity, and from that generalize it to the stress energy density of a perfect fluid in general relativity. This technique, this way of building stress energy tensors, it's common. Actually, it's a pretty common technique, saying like, all right, I have really good reasons to know it in a particular frame, and I know from there how to write it from that frame, how to generate a covariant expression that is valid in all frames. And from that, I'm going to generalize it. This is common, and it's good that we see it. Now, there's a lot of physics in doing this, so let's pay attention to the different meanings of the components of the stress energy density. Now, I have here the T00 component that we saw was literally an energy density, right? Then we have the 0I components that you can interpret into different ways, the momentum density, but that's the same as the energy flux in the I direction. There could be some energy flux in the I direction because of two reasons, right? You can have like physical motion, something is moving from here to here and taking the energy from here to here, or they could be that the microscopic constituents are the ones that are taking it, not the macroscopic object in itself. So if we were talking about a fluid, that is equivalent to things related to the conduction of heat. Heat is moving like this kinetic energy over here that is transported here conductively, right? Okay. Now, what about the Tij components? The Tij components are slightly more complicated, but they do represent, look, if you actually see that this is the energy flux in the I direction, when you go spatial, what you get is the flux of the I. It's kind of, this whole thing, you can think of it as the flux of form momentum, the whole thing, the flux of form momentum in the direction perpendicular to the component that you're considering. So the T mu nu is the flux of the muth component of form momentum in the direction across the surface perpendicular to the nuth direction. So in that particular way of seeing it, you see that the T0I is the energy flux in the I direction, and the Tij represent the flux of the ith component of linear momentum in the j direction. Remember what flux is. Flux of something is the amount of something going across surface per unit area per unit time. All right? Now, in particular, if you look at the diagonal components have units of pressure, because indeed, the flux of linear momentum in the x component across the surface perpendicular to the x component is the pressure that is exerting on that surface. That's just out of dimensional analysis. Here we're going to use natural units again, and we're going to try to give the values for this stress energy density for a perfect fluid. Now, what is a perfect fluid? A perfect fluid is a fluid with no viscosity and no heat conduction. Let's assume that my fluid lives in a particular region of space-time and that I'm going to look at it from the comoving frame. The comoving frame is the frame when I see zero total momentum for the fluid. So the fluid is not moving from one place to another. All right. Now, in the comoving frame, what are the different components? Let's begin with the T00. T00, I write equal to rho. Rho is what I call the energy density of the fluid. We're natural units. So this energy density of the fluid, you can think of it as mc squared divided by the volume that the fluid occupies. So it's literally, in natural units, is the density of the fluid, literally. All right, so what about the T0i component? The T0i component is also fully determined in the comoving frame. In the comoving frame, the fluid doesn't move from one place to another. So the only way that energy can flow from one place to another is through heat conduction. And I don't allow heat conduction. So this is zero. Let's look now at the spatial components. In fact, I'm going to write here the T mu nu, and I'm going to have here the T00, which is rho, as we discussed. I'm going to write this separation here. This is 0, 0, 0, as we found. The TOI are 0, 0, 0. It's a symmetric tensor. And let's see what the TIJ are. Now, the diagonal elements. In the diagonal elements, what we have is the pressure of the fluid. It's literally what is the flow of the momentum of the fluid in the direction perpendicular of the direction of the momentum I'm looking at. That is the pressure that the fluid exerts. So I can write maybe a Px, Py, Pz, then being the pressures exerted to the surfaces perpendicular to the x-axis, the y-axis, and the z-axis. All right. Now, how about the Tij that are non-diagonal? What are those? Let's understand what it is. The flux of ith component of linear momentum in directions that are not the same direction. So imagine a pipe like that. And imagine that my fluid has some velocity here, like this. And what happens? Well, you know that there's a mechanism called viscosity that makes, the velocity get transmitted. If I induce velocity here in this direction, then I'm going to pull from the layers that are right below, right? And I'm going to have a profile of velocities. And that profile of velocities precisely, if I have momentum in this direction, is inducing momentum in the directions, in directions that are different from the direction of propagation. So you see, there will be a flow of momentum transmitted from here upwards in the direction of x. So I have a flow transmitted in the y direction of momentum in the direction of x. This is literally what the non-diagonal components of the spatial part of the stress energy density are accounting for. Now, we know that this fluid is perfect, has no viscosity, and therefore, these have to be all zero. Said in a different way, without viscosity, there cannot be any drag from one layer of the fluid moving, dragging the layers around it, so there's no shear stress, so there's no flow of momentum in directions that are perpendicular to the direction of the momentum. All right, that's it. Let's go back to the video. All right, so let me write it here. Tij with I different from j is equal to 0. But there's more, because I can do rotations in space, right? Now, if I have a matrix like this and I do rotations in space, imagine that I am in the comoving frame, but it's also a comoving frame if I rotate, right? If I can rotate myself and it's still comoving. I'm not seeing the fluid start move because of that. It's just, a rotation. I just see it with a different perspective in terms of what I call my angles are just different now. But if that's the case, a matrix that is diagonal is not diagonal under rotations in general. A rotation takes a diagonal matrix into non-diagonal matrices. There is only one family of matrices that if they are diagonal in one basis, they remain diagonal under rotations. And those are multiples of the identity. So what I know is that the Tij, the diagonal elements Tii, they cannot be different. They have to be the same. The pressures cannot be different in the different directions. Because if it were the case, then there would be a comoving frame that is rotated with respect to the one where I see it being diagonal, in which it will become non-diagonal. So the fluid has no viscosity. I cannot say that the fluid has viscosity, no viscosity in one frame, but has viscosity in other frames. If I rotate a little bit, suddenly the fluid has viscosity. Oh, it's burning me with all the heat dissipation of viscosity. No viscosity. That would be physically stupid, ridiculous, outrageous. So we conclude that the spatial part of the stress energy density has to be a multiple of the identity. I can write that this thing has to be P delta Ij, a multiple of the identity. All right, so we have determined the stress energy density in the comoving frame. Nice. What good does that do for us? We don't want it in a particular frame. We want a covariant expression. Can we find a covariant expression? Let's see. The process is the following. Find the only expression that can satisfy these two conditions. A is covariant, that is, it's a tensor expression, and B, capture the right values in the comoving frame. If I find that, I found the stress energy density. Now, the best way to find it is in special relativity, right? Because in special relativity, the metric is diagonal and simple. And then we use the dirty trick to transform it into a general relativistic expression. So let's begin the constructive process and see what we can do. How many things that we know that are covariant can we use? Well, we can use maybe we can use the for velocity of the fluid because it's easy. U mu, I'm in the comoving frame, so the for velocity is going to be 1, 0, 0, 0, right? The fluid is not moving, it's just moving in the future in time. So in the comoving frame,
that's when you're like in comoving frame, right?
The for velocity is just 1, 0, 0, 0. Awesome. What are the things, and this is covariant, this is a for vector. What are the things I know that are covariant? Well, the metric tensor. I know that the metric tensor is eta mu nu, and I can represent that as a matrix as minus 1, 1, 1, 1, right? Okay, wonderful. Now let's try to use these two. First thing that I want, okay, I want to have p's in the diagonal, and I have the metric tensor. Let's try that. All right, let's make a first guess. First thing that I want to have p's in the diagonal. Well, not in all of them, in all the diagonal elements, but in many of them. So one first idea, perhaps, is write t mu nu. Oh, that thing I'm going to write as p times the metric tensor, right? Because, if I do that, I got almost what I want. I'm going to have p times, like, minus p, p. Well, p is what I wanted here. I don't want a minus p there, right? But, I have I have a lot of diagonal elements. I just need to somehow substitute one of them. What else do I have to add? Well, yes, I know something that only has a time component, the for velocity. I can use the for velocity to build this. Let's see. I added a term here proportional to 2 copies of the for velocity. You can think of this as the components of the tensor product of the for velocity with itself. Okay? Now, what does that do? Let's see. The 0, 0 component would be minus p coming from this minus 1 plus rho plus p because this thing is 1 and 1. Nice. So that would cancel the p, the minus p that I had here when I multiply this thing. If I write it in matrix representation, it would be minus p. And this thing that I'm adding here would be rho plus p, 0, 0, 0. So if I add the two of them, I get this stress energy tensor. Wonderful. I found it. This expression is covariant, metric tensor for velocities. I found a covariant expression that gives me, in the comoving frame, exactly what I want. Wonderful. So this is the only covariant expression that gives me what I want. So I know this expression is the right expression for the stress energy density of the fluid. This is a tricky way to obtain it that I hope to discuss with you in the live sessions. You could have obtained it from first principles and continuity equation for the fluid. Of course, knowing some fluid dynamics that I didn't want to introduce. But this is common, and this is the way you usually do it, actually. All right, now all that we need is to make it general relativistic. But for that, we have our dirty trick, right? That what it does is substitute the expressions that are covariant in special relativity. We know that in general relativity, special relativity is true locally. So it's very easy to do the substitution of, metric, a flat metric to general metric, and partial derivative to covariant derivative. If we do that, we obtain this. And this is the stress energy density in GR. This is in special relativity, and this is in general relativity. So this is the stress energy density of a perfect fluid in a curved space-time. Now, things that you may wonder, why did you lower the indices? Because I wanted to. I have no reason to. I could have written them up, but I have a metric I can lower and raise. So the only change is that the eta now is a g, and that's the only change. Now, let me talk about something. Fluids are also characterized by something called equations of state. The equation of state of a fluid, I mean, you remember the equation of state for an ideal gas and things like that, right? The equation of state is a relationship between pressure and density. Equations of state set a relationship between the density and the pressure of the fluid. For example, you can have what we call free dust, which is a fluid made of particles that don't interact with anything. Therefore, pressure is 0 for that one. Or you can have an ideal gas, typical P times V equals nRT, so only putting the V on the other side, and then you get a density in there, etc. Now, the equations of state are extremely important, and we will see, and we will discuss a little bit how important they are when we do cosmology and things like that, because the equation of state of the fluids that actually source gravity for things like the accelerated expansion of the universe could be the difference between a universe that is expanding, stopping and contracting, expanding and asymptotically stopping, expanding and accelerating the expansion, or expanding so fast that it will rip everything apart, including you and me, eventually. So those differences are actually due to what the equation of state and you want. I mean, how the interaction between how the relationship between the pressure and the density of the fluid is established by the internal dynamics of the fluid. Okay? All right. Let's do one more thing. I'm gonna get these equations, and I'm gonna separate these equations into, same as we did with the, remember with the Lorentz transformation for a particle and acceleration transformations. We can split the equations of motion of the fluid into components that go in the direction of the velocity and components that are perpendicular to the velocity. Let's do that. All right, so we have the equations of motion of the fluid, the divergence of the stress energy density equal to 0, and I can expand it, as I did here, interval using chain rule. Now, this equation, now I can project into the longitudinal component to the for velocity and the perpendicular one. The longitudinal component I just get contracting with the for velocity. And the perpendicular one, I need to apply the projector on the direction perpendicular to the vector. Remember that if I have a projector over a vector v from your algebra, you know that the projector that is orthogonal to v is going to be the identity minus the projector of v, right? That's the usual in a Euclidean space, that's what you would get. However, remember that the for velocity has negative norm. So then that's why you have a plus. You have the identity, the projector is the identity minus the projector on the direction of the velocity. But you need the plus because you're going to get a -1 when you contract to time like, you're going to get a negative number when you contract to time like projectors. It's very easy to prove that the two projectors are orthogonal. Let's see. This is the projector on the direction of the velocity. This is the orthogonal projector like this. When I multiply the two, you see what I get. I get the delta that changes the c to a b, and I get the a and the b here, and then I get the norm of the for velocity, which is -1. And therefore this thing is 0. So indeed, this is the orthogonal projector to this projector. This is the, if you want, the ket bra, right? The equivalent in the algebraic structures that you use in quantum mechanics. It's a ket, that's a bra. That's a projector. And this is the orthogonal. This would be the equivalent to identity minus the ket bra, right? Minus the projector. But of course, being careful with the signature because this is a Riemannian manifold. All right? So if you apply UV to this equation, contracting with UV, or you apply this to this equation, you're going to get these two. I think it's a really good exercise. There's a couple of tricks they need to use. For example, proving this identity would help. Proving that UV, covariant derivative A, UV, is equal to 0 could be a good start. Prove that first. And to prove that, you may want to use that UV equals -1. Maybe try differentiating both sides or see what happens. I mean, play with it. I don't want to tell you the solution. I think it's a good exercise to actually obtain these equations from this one, contracted with UV, and applying this. All right. These are the equations that generalize the continuity equation that you've seen in fluid dynamics, if you have seen fluid dynamics. This is the continuity equation associated with the conservation of energy or conservation of mass, if you remember your fluid dynamics. And this is the one related to the continuity equation of the conservation of linear momentum in the fluid. We can do a particular example and see what these equations tell us. Let's take the equations of free dust. This is a completely non-interactive fluid. That doesn't interact with anything. It's made out of like particles of dust. What would we get in that case? So in that case, we get the conservation of energy is very trivial. It's a conservation of mass. And most importantly, the conservation of linear momentum is translated into a geodesic equation. So of course, a fluid that has no pressure follows geodesics because it's a lot of free particles, all of them following free trajectories that in general relativity are geodesics. So indeed, you get the geodesic equation for a free dust. All right. In general, you're going to get more complicated equations of state. If the equations of state only involve pressure and density, we call them barotropic equations of state. There could be more variables, of course, and that would make things more complicated. When you see how stars gravitate in general relativity, that you will probably do in an assignment, will you see that the equation of state does play a role? What is the material that makes the star plays a role in how it behaves gravitationally, indeed. All right, now that we've seen the stress energy density for a perfect fluid, which is something that we use a lot in relativity, above all in cosmology, it's used a lot to model the stress energy density of the fields that fill up the universe. Now we're going to talk about something called energy conditions. The last concept we're going to deal with in this video is the so-called energy conditions. So what are energy conditions? Energy conditions are not part of general relativity. Let me tell you that. Generally, energy conditions were imposed on top of general relativity to avoid problems. They are seemingly reasonable hypotheses or assumptions, if you want, that make sense perhaps to postulate, and the advantage that you get postulating them is that you get rid of a lot of monsters. What do I mean by that? Einstein equations produce monsters. If you solve Einstein equations, you can find solutions, depending on the stress energy density that you put in, you can find solutions that have weird stuff. For example, you can have naked singularities. That's horrible, because if you have naked singularities, your theory doesn't have predictive power. There are other things that are very troublesome, like closed time-like curves. Time travel. General relativity in its guts allows for time travel to the past, as in like going back to the past. And we can discuss that in the live sessions too. How do we understand in rigorous physics closed time-like curves? How accurate is sci-fi portraying the effects of closed time-like curves, if at all? So we can discuss that in the live sessions. Also, wormholes, warp drives, like the Alcubierre warp drive. That's a solution of Einstein equations that allows you to effectively travel faster than light without any Lorentz construction effects. As in, like I'm in the middle of a warp bubble and I'm not moving, and my proper time is the same as somebody at infinity, but there's some bubble, something happens in the bubble, like some strong curvature in the bubble, so that the bubble is kind of effectively like an effective motion of the space-time background with me sitting stationary in the middle of it. And the effect is that if the bubble is created, moved, and then dissipated, now I can go to Alpha Centauri maybe in one day. A warp drive, that's the Alcubierre warp drive. That's a solution to Einstein equations as well. People were most worried with singularities though. And we then arrived to Stephen Hawking and Roger Penrose. Roger Penrose and Stephen Hawking, working together, developed what are called the singularity theorems. The singularity theorems tells you under what conditions you would have an okay causal structure for your spacetime. No monsters like naked singularities and so on, and also accessorily no time travel, no warp drives, no faster than light stuff. Things that are kind of reasonable, I guess. We'll see. Now, the conditions that we have here are conditions that are imposed on the matter fields, on the TNUs, on matter. And we're going to talk about 4 energy conditions. 4 energy conditions that are different conditions, and all of them can be used to avoid monsters in one way or another. Some of them are stronger than others. We will go through them first. We will explain what they are. We will see which ones imply which others. We will see what they mean for vector fluids, which I already have here, but I won't talk yet about it. And we will summarize the interpretation of them with modos. Let's do it. First of all, let's read it out. So the weak energy condition. What's the weak energy condition? It tells you that the stress energy density satisfies the weak energy condition if and only if the TAB contracted with VAVB for any future directed time-like vector is larger than 0 or equal than 0. What's that telling us? That's very easy to interpret. Remember that a time-like vector, somebody's time-like vector, like if you see a time-like vector, that's somebody for velocity, right? Because the for velocity of any person in their own frame is 1, 0, 0, 0, 0. The for velocity of any person in his own frame is going to be 1, 0, 0, 0, correct? That means that that for velocity 1, 0, 0, 0 in a different frame will have a different set of components, will still be time-like. You can always twist your axis if you want to make any time-like vector somebody's for velocity. You can always go to the frame where that time-like vector is the for velocity or proportional to it. So what this means is that what you're demanding here is basically that for all possible observers, the T00 component has to be positive. If you remember what the T00 component was, is the energy density. So basically you're forbidden with the weak energy condition. You're saying kind of, I won't allow things, negative energy densities. I don't want negative energy. I disallow it. I don't like it. Out. So let's write a motto for the weak energy condition. The weak energy condition tells you there's no such thing as negative energy. Nobody will ever see a negative energy density. Go home. All right, let's switch to the strong one. The strong energy condition is more complicated to interpret at first sight, but it tells you something about the curves that matter follows. It's telling you that the trajectories of matter, the trajectories of the flow of energy and momentum of matter, if you consider a bundle of those trajectories, as you move towards the future, they're going to get closer to each other. So basically it's telling you that the deviation, the acceleration they would experience through gravity is going to make them closer. So basically this condition is telling you that as you move, if you have a beam of energy propagating as it moves towards the future, it's going to get attracted, it's going to get, all the different beams, if you want, are going to get attracted to each other. So basically, we can summarize the strong energy condition with the following motto. Gravity is attractive. There's no such thing as repulsive gravity, anti-gravity, or whatever. That's the motto of the strong energy condition. No repulsive gravity. Go home. All right, let's go with the dominant energy condition. The dominant energy condition tells you that these are the energy flows, as we saw before. So basically, they're telling you that the velocity at which, if you want, energy propagates has to be time-like or null or 0. That means that, I don't allow for superluminal transmission of energy. I forbid that there is a stress energy density so that I see faster than light, so that thing that I talked about with the word drag would violate it, faster than light propagation of energy, which kind of seems reasonable. Let's just write the motto there. Energy must not flow faster than light. The dominant energy condition tells you no such thing as faster than light flows of energy. Go home. All right. Now finally, the null energy condition. That's arguably the most difficult to give a motto that is catchy. That tells you that you can think of it as a limited case, if you want, of the weak energy condition. That tells you that, for very fast, in the limit of really, really fast, future-directed time-like vectors that become null, then something like the weak energy condition has to be satisfied. In reality, if we want to give it a motto, it would be something like this. Shear stress experienced by propagating light must not be negative. Again, you can think of it as a weaker version of the weak energy condition. In fact, these conditions are not equally strong. They imply each other in some ways. Let's see the chain of implications here. So you see that the most demanding of them all is the dominant energy condition. The less demanding to matter would be the null energy condition. And we see that the strong implies the null, but the strong is unrelated to the weak and the dominant implies the weak and implies the null. All right. Now, for a perfect fluid, of course, remember, these are conditions on matter. We're saying matter cannot be whatever you want. Matter, to be reasonable, to forbid monster solutions to Einstein equations, needs to satisfy at least some of these conditions, at the very least, because otherwise you're going to have monsters. Now, ideally, you would satisfy all of them, right? I mean, then you're super protected. Now, you can actually check what are the implications, what these equations mean, what these statements mean for perfect fluids. I will give you the solution because I promised you there will be an assignment where you will have to derive this, the implications of these conditions for a perfect fluid and a little bit more. So I won't tell you how to get them. I will ask you to tell me how to get them. But here it is. For a perfect fluid, the null energy condition means that the sum of the pressure and the energy density has to be larger or equal than 0. The weak energy condition implies that certainly the stress energy density, certainly the energy density has to be larger than 0, and also that the sum of P and rho has to be larger or equal than 0. The strong one implies that rho plus P has to be larger than 0, and also rho plus 3P has to be larger or equal than 0. And the dominant implies that rho has to be larger or equal than P. Let's look at these modules. There's no such thing as negative energy. Seems reasonable. Why not? Of course, there's no such thing as negative energy. I would believe that. Why not? In principle, gravity is attractive. Duh, yes. Gravity is, I haven't seen anti-mass the same way we have anti-charge. So yeah, no, there's not two masses, right? Two positive and negative masses in a way. In Newtonian even, it's kind of easy to get behind that one. Energy must not flow faster than light. Of course, we are the speed of light inquisition. Nobody expects speed of light inquisition. As in like, but what happens with causality otherwise, right? I mean, oh my, I like this one. It's okay to have that one. Well, the weak is the weakest of them all. It's more difficult to experience, but this one seemed like very reasonable. This one is actually asking less from matter than this other, so they seem like pretty reasonable. And they were for no classical matter that we know of can violate these energy conditions. Now the problem comes when you do quantum field theory. When you start doing quantum field theory, then you discover that quantum field theory there are states of quantum fields that can violate energy conditions. And in particular, you know which one you can violate? You can violate the null energy condition. The weak very easily, the null a little bit more difficult, but you can violate the null. You know what that means? That means that quantum fields can violate all energy conditions, because if you violate the null, you cannot fulfill any of the others, because the null is implied by all the others. So that is big. Quantum fields violate energy conditions. In fact, quantum fields, even something like a squeezed vacuum, squeezed state of light, for those of you who have seen any quantum optics, the squeezed vacuum has negative energy density somewhere. If you create really a proper squeezed vacuum, not the one that you would do in the lab very likely because you have a lot of noise, but if you get a vacuum and you squeeze it, that thing has negative energy densities, also positive ones. So yeah, quantum fields can violate energy conditions. They cannot violate energy conditions infinitely. There's limitations, so you can violate it depending on how much. If I want to violate in this room, then I'm only going to be able to have a little tiny bit of negative energy. If I want to violate it in my hand, then I can do more negative energy. In principle, if I make it really, really tiny, the region, I can have as much negative energy density as I want and negative energy as I want. But you have to pay a price for it. For all the negative energy that you generate in that state, you need to generate also positive energy density somewhere around it. And there's no escape for that. There's something called the quantum interest conjecture. It's actually a theorem in many cases, but it's called still conjecture because it's not fully proven everywhere. But the quantum interest conjecture tells you that not only you have to generate as much positive energy as negative, which makes sense, and you do have to because you have a quantum field theory that has a vacuum state, then if you create negative energy density here, you at the very least need to create as much positive energy around so that you are not falling below the vacuum because the vacuum is the ground state of the theory, the one with the lowest total energy. But not only that, the quantum interest conjecture actually tells you that you have to put more positive energy on top of the negative energy that you created to overcompensate for it. You're forced to it. It's a fundamental law of nature. Now, we can get into a discussion of what it means for a quantum field to violate these energy conditions, because quantum fields, the stress energy density suddenly now is an operator. And what does that mean? Because I cannot have Einstein equations, right? One side with operators, one side without. Oh, but you can have expectation values. Okay, so if you source Einstein equations with the expectation values of the quantum fields, then you can violate energy conditions. So maybe, can you do a warp drive with those? Can you do a time machine with those violations? Well, in principle, yes. In practice, well, we need to discuss it, because in practice there are limitations that you can have as to how much positive energy you can afford to spend? How stable are those? Are you going to have horizons that are going to evaporate and there your warp drive is going to fry itself? Well, those things, are they even stable? So those things we're going to have to discuss in a live session. You would imagine problems with a warp drive, right, of instabilities and accumulation of energy if you go faster than light and things like that. We will discuss all those if you want in live sessions. I really hope there's a lot of discussion about it. But at the very least, you now know that these things are not part of general relativity. They're reasonable assumptions on matter that you do to protect yourself from the monster solutions with time travel, with faster than light travel, the monster solutions with crazy naked singularities, the monster solutions of general relativity. You create these walls to protect you, say, no, let's not let matter do that because woo. And then suddenly quantum fields violate them. And quantum fields seem to describe matter the best way we know. So what's going on? Super interesting stuff. That's one of the things I do research on. So we can discuss a little bit about all these things, and I hope we do in the live sessions. For now, I think I'm going to leave the video here. I'll see you in the next video to continue with general relativity. Until then, take care.